Okay, we now have our second speaker for this morning. It's Stefan Hollands from the University of Leipzig. I'm very glad that he will give a talk on black hole interiors.
All right, it's an absolute pleasure to be here in such a marvelous city and such an absolutely stunning conference venue, which shows that we academicians were valued in places like Rome already a few centuries back. My talk is about black hole interior. Now, if you look at this map, you get the clear idea that the cartographer thought that the end of the world was surely a dangerous place inhabited by monsters, such as those fish at the bottom. While our conceptions about geography and even cosmology have changed greatly since this was drawn, it's perhaps a bit too rash to look back at those times condescendingly, because even with in modern science, that is theoretical physics, we still believe that the end of the world is a very dangerous place. Now, however, not anymore located at the distant oceans on Earth, but at the beginning of time during the Big Bang and inside black holes, because we believe that at least general relativity suggests that those places are inhabited or are described by a singularity, a space-time, a set of space-time points where definitely something very terrible happens, maybe not monsters, but we should surely not try to go there. Now, this talk is not about the beginning of time, the Big Bang singularity, but in some sense, the easier case, the less mysterious case of singularities inside black holes. And I've drawn here for you a kind of diagram that in general relativity is very common to draw. It's called a Penrose diagram. So if you do not have a background in general relativity, let me say a few words how you should read this kind of diagram. It's supposed to depict a four-dimensional space-time, but in the plane, so we drop two space-time dimensions. The space-time that we are considering have spherical symmetry. So in this diagram, we suppress all angles so that at each point in the diagram, in fact, is a two-sphere. And also, we draw the time arrow always upwards so that the upper part of the picture is further to the future than the lower part of the picture. The spatial directions are the radial coordinates, so to speak. The picture shows a region 1, which is the outside of the black hole. It looks like a finite region, but there are places indicated by the script I plus and I minus, which represent the infinity. So the other aspect of this kind of diagram that makes them useful is that they put the infinity in a finite place by a conformal transformation. So you can draw the infinity on your picture, in your finite picture. So we have the exterior of the black hole bounded by the infinities where you will go if you travel on a spaceship forever, preferably at the speed of light. Then we have the region 2, which is the interior of the black hole. It's the place that you arrive at if you were to cross the line H, which separates the outside and the inside of the black hole from each other, and which is called the horizon. Do I have maybe a pointer? Yeah. Okay, so this is the horizon. So when you travel inside like this bluish person, you will cross the horizon at which nothing particularly bad is going to happen. After which you're going to cross another kind of horizon called CH, which stands for Cauchy horizon. And if you travel further, at least that's what the picture suggests, you reach the end of the world, not inhabited by monsters, but by this wiggly line, which represents a terrible singularity where certainly you are going to die. Now, if you are familiar with this type of diagrams and with basic laws of wave propagation, you will note that there's something strange about this region 4 beyond the Cauchy horizon, the region that you're going to enter according to this picture before you hit the singularity. And that is supposed to be indicated by the following. If you, let's say, pose initial condition on a time 0 in quotation marks slice like the green one here, then you can predict the evolution of a wave or whatever equation similar to that within only regions 1 and 2, but you cannot predict what's going to happen in region 4 unless you impose a boundary condition on the singularity. From a physical perspective, you should not do that because the space-time singularity is just a hole in space-time. There's nothing, there's no sensible boundary condition to put there, unlike in a conductor where you say the boundary is a conducting plate, and you can imagine what sensible boundary conditions are. There's nothing of this sort. So there's a lack of predictability in region 4, and that kind of observation is addressed by an old conjecture due to Penrose called the strong cosmic censorship conjecture, which is going to be a main topic of this talk. SCC, I'm going to abbreviate it. And the main hypothesis or the proposal is somehow that region 4 is not there in the first place, and that the singularity should in some sense be already right here. So how the argument works is as follows. You say, well, the heuristic argument, you say you consider two observers. One is, the red one is a more prudent and cautious observer who decides to propel him or herself in such a way as to stay clear of the black hole. And another more daring and experimental observer, the blue one, who dives right into the black hole. And the point to note is that if observer red sends periodic signals according to his or her proper time at a constant frequency, because observer blue will cross this surface at a finite amount of time, necessarily the signals that he receives will pile up. They will appear, let's say, on his smartphone or whatever receiver more and more frequency, and in fact infinitely frequently as he crosses this Cauchy horizon. Now, we think of this is a very robust argument. It would likewise apply to wave or whatever disturbance. So one thinks that due to this phenomenon, the transverse derivative in this kind of direction across the Cauchy horizon of any physical field, phi, will terribly blow up. And therefore, this nice picture, it would be unstable to perturbations, meaning that perturbations would, in effect, put the true singularity already somewhere like here, and region 4 is not there. So this very strongly affects our understanding, therefore, of black hole interior. Whether this so-called strong cosmic censorship conjecture is true or not. This is just a heuristic argument. It doesn't prove or disprove that fields really behave in this way. They could blow up, but maybe only in a very mild and harmless way, so that this picture would still remain intact and you would still have region 4 and the problems associated with it. So therefore, a more mathematical formulation of this conjecture is warranted, as given, for example, by Dimitris Christodoulou in 2008. And according to this reasoning, which is is strongly informed by his insights about the nature of solutions or distributional solutions to the Einstein equations. He says that what the conjecture means is that a generic initial datum, or for a generic initial data, a non-linear metric perturbation caused by some disturbance around on this initial surface should be inextendable as an H1 log. So this is a Sobolev space, meaning one derivative in L2 across this Cauchy horizon. So that's his notion of singularity. And if that's the case, so if the solution isn't in H1 here, then indeed something terrible is going on. You can't continue the solution even as a weak solution to this region 4, and therefore region 4 doesn't exist. So that's Christodoulou's formulation. It's just a formulation. It doesn't say what actually is happening. It's just say what this means mathematically. And maybe a more physical way to formulate it is if you restrict attention, if you both scalarize and linearize the Einstein equation. So you have, instead of the nonlinear Einstein equation, you just have a linear equation for a scalar field as either a model or a model for matter on this space-time. You say that this means that the VV component of the stress tensor, where V is a coordinate pointing this way, should not be an integrable function. So in this case, if this is not an integrable function, it means the flux blows up sufficiently here so that you can't extend the space-time beyond the Cauchy horizon, meaning that the picture is suggesting the wrong thing, and the true singularity should be somewhere like there. Okay, it's still just what it means. There's no actual investigation yet of how exactly a solution behaves there. It's just what you would need for the strong cosmic censorship conjecture to be true. Okay, so now I'm going to move on to a slightly different space-time to look at this question, which is the so-called Reisner-Nordström de Sitter space-time. So it represents a charged, spherically symmetric black hole with a cosmological constant. The cosmological constant results in the presence of yet another region, region 3, separated from the exterior by a cosmological horizon. We shan't be interested in region 3 really, but still in region 2 and 3. But the cosmological constant does some mathematically nice things to this problem that makes it more tractable. And also there is a positive cosmological constant in the actual universe. So it's not completely unreasonable to actually move to this case. So the metric, if you haven't seen it, it looks just like the easiest, the simplest possible black hole metric. It has a line element like so, where the only non-trivial feature is this function f of the radial coordinate, which is this kind of expression here. And horizons occur where this function f is 0, and we assume parameters q, charge, m, mass, lambda, cosmological constant, so that we have 3 distinct roots of f, which give 3 distinct horizons: the cosmological horizons, the black hole horizons, and the cosmological horizon. If you're not in this regime, you have a naked singularity, which is unphysical anyway. So that's the usual assumption. And frequently, I'm going to use null coordinates. V goes at northeast, and U goes at northwest in these diagrams. So it's the V coordinate that is going this way across the Cauchy horizon. It's the most relevant for this talk. In black hole physics, you understand that with such a metric, you get so-called surface gravities for each of these horizons, which are closely analogous to a kind of temperature. So now come the first mathematical results, which, well, there are many mathematical results on the behavior of solutions to wave equations on black hole backgrounds. In fact, there's a whole community investigating such questions, the community of mathematical relativity, or a a relatively large subset thereof. And I'm not doing any justice to the huge body of work done in this community, but I'll mostly refer to this one paper which addresses the precise background that I'm considering. And this paper showed how a field that comes from nice initial data here behaves there. And what these people, this field is called phi. And what these people showed, Hinz and Vagi a few years back, is that the solution is in a Sobolev space with 1/2 plus beta fractional derivatives. And so Christodoulou said that cosmic in H1, so cosmic censorship will be violated if somehow you could show that beta was greater than 1/2. Another feature, another thing proven among other many things in this paper is an expression for this beta, and it's a quotient of the temperature of this horizon. And in the numerator, you have the so-called spectral gap for this operator. It's a kind of width of a resonance-free strip for the radial equation. So it has to do with the, in some sense, resonances of this operator or an operator very closely related to this operator. And so this alpha is, you think of as a decay rate for waves in region 1. And it's known how, in principle, to calculate this alpha, but unfortunately not analytically. So people did a numerical analysis of what this alpha was. And what the people found was that indeed, beta is greater than 1/2, at least if you choose the parameters right, if you consider a black hole with a sufficiently large charge. So this is a very significant physical result because it says that from a classical viewpoint, you have region 4, there's not a strong enough singularity of wave perturbations here. So you will, according to this result, enter a region where causality fails because you do not know how to predict what's going on there from initial data. So this is a very serious physical problem, and it's a problem for all these type of physical black holes. So these are not some fantasy theoretical physicist toy model, but black holes closely related to this one with, a practically identical looking Penrose diagram are thought by everyone, I think, to be astrophysically realized. So this conjecture seems to fail. This was a pretty big thing. So that suggests that you should look at quantum fields. Why should you look at quantum fields? So again, when the strong cosmic censorship is violated, it means the energy momentum flux is across the Cauchy horizon still a locally integrable function. That's what Christodoulou, that's the criterion. So it has a rather mild singularity. So classical effects are not sufficiently strong. So you can ask whether quantum effects could possibly be stronger. So this is, I should emphasize, is a crazy idea because nowhere in the real world, except maybe in cosmology, are quantum effects stronger than classical ones. And this is supposed to be a low energy kind of situation, not a particle accelerator type situation. So the idea that quantum effects, let's say the fluctuations of the electromagnetic field caused by these candles there should be much stronger than the classical effect is at first sight ridiculous effect. However, there is geometrically something going on, and it's not it is not totally unreasonable to ask that question. It's a free world, so you can ask any question you want, but it is not a totally unreasonable question if you think about it a little more. So mathematically, what you would try to show is that the expectation value of the quantum stress tensor, the component analogous to the one you compute classically, in a generic initial Hadamard state, it's a kind of technical term, meaning basically a smooth initial state, is not an L1 function. So its singularity is stronger. And sort of the reason that you may think there's a shot is that a quantum state contains virtual particles of arbitrarily high frequency. And as we've seen, this strong cosmic censorship is about a blue shift phenomenon, a phenomenon related to shifting of frequencies. And if you have frequencies that are already very high, then if they get shifted even higher, this may cause a large flux of energy momentum near the Cauchy horizon. Anyway, so you may think you may think this, or you may think that, and at the end you have to submit this to a rigorous analysis, which is what mathematical physics is about. So what we showed in a paper from about 2 years ago is that for a generic initial state, or a generic well-behaved initial state, which is basically, should be thought of as basically all physically relevant initial states, you have a behavior like this. You have a very strong divergence where V is a coordinate that's 0 at the Cauchy horizon. You have a very, very strong divergence plus a mild divergence, where this mild part depends on the state, and it has beta minus 1/2 fractional derivatives in L1. So Christodoulou says that you just have to be in L1, so this is even better than what Christodoulou would still consider a very weak singularity. So this way of writing it is to indicate that this really is the dominating singularity, which comes with a coefficient C and this very strong divergence. So now the point is that C can be calculated in principle by some mode integral expression, where the number density, if you like, you can interpret this, is determined by a scattering problem, which I'll describe, and has no dependence on phi. So the important point is this divergence is a universal effect. It does not depend on the choice of initial state, which is only buried in this subleading piece. So if you were to write out H bar, so sometimes it's good to write out H bar with theoretical physics. So this would have an H bar in front, and this kind of wouldn't. So it's a purely quantum effect, this thing. And you see that it overwhelms totally the behavior that you would already have for a classical field. So it's a surprising finding that in this situation, quantum effects totally dominate the classical effects. Even if you start out with a state representing like a classical object, like a table or a beam of low energy electromagnetic radiation, which has usually a nice classical description. At the Cauchy horizon, the quantum effects totally dominate everything. Okay, so I wanted to say how this ends are supposed to be calculated. It's a simple thing in principle. You take the Klein-Gordon operator for this background, it's a sort of D'Alembertian with the metric minus the space, the mass squared of the field. You make a simple-minded mode ansatz, which is suggested by the symmetries of the space-time. The non-trivial behavior is in the radial function, for which you get this kind of 1D Schrödinger equation with a certain potential. You can just write it down. I don't want to do it. And it's a potential that at each of these horizons in a suitable coordinate R star decays exponentially. So it's a totally standard scattering problem in a radial coordinate, which is defined so that it's minus infinity here, plus infinity there, and then again plus infinity there. So in fact, you have two scattering problems somehow, one in region 1, one in region 2, and physically what it corresponds to, reflection, corresponds to a particle, a quantum particle or a mode being reflected across the horizon, and the other one going through here, and likewise in this region. So you compute the scattering coefficients, T and R, transmission and reflection, just a totally standard, in principle, thing you learn in your quantum mechanics lecture, and you get these coefficients, and then from that you get N, and then from that you get C, and C is the coefficient of the singularity of the stress tensor. This is the thing we're after. Okay, so there's this is a nice, is an interesting equation. It's a Hoyne equation. It has lots of interesting relations to many things in mathematical physics. But to answer this question, really, you just need to calculate these, and you could just do it numerically. The theorem proven is a mathematical theorem, but the practical evaluation of the C is a numerical task. So we evaluate it numerically, plotting the C, ignore the units and ignore what's on this. So this is the C, the coefficient of the energy momentum flux at the Cauchy horizon. This is Q over M. Q over M is restricted to values a little less than 1. Otherwise, you have a naked singularity and the whole thing doesn't make sense in the first place. So you'd see two things. Maybe don't worry about the shape. But what you see is it's sometimes positive, it's sometimes negative, and at saturation, where you reach the end point of your black hole family, beyond which you would have a naked singularity, you'd overcharge it, you destroy it, it goes to 0. So this is important in two ways. So in this region, you get a positive energy flux through the Cauchy horizon from quantum effects, which is the thing you expect. But in this region, you get a flux of negative energy density through the horizon, which is a totally non-classical behavior. And furthermore, at this point, the flux goes to 0. So you can't somehow push the black hole over this extreme limit by quantum effects. So there's somehow inherently, at least for these parameters, a safety switch. So the quantum effects don't destabilize the black hole fundamentally, but they would change this horizon, this Cauchy horizon, to a singularity. And basically, as an observer in this parameter range, you get crushed to death at the Cauchy horizon. And in this, so you become a spaghetti, very long and thin. And then in this parameter range, you get, how do you say, it's like you get pulled apart. Also not very nice. And of course, this is just the coefficient of the truth of the singularly behaving energy momentum flux. You can also plot the dependence of this on the mass, and you somehow see that with the mass of the particle, and you see that when the mass of the particle increases, it's somehow intuitively harder to create particle-antiparticle pairs because they have a larger mass, and so this effect also becomes smaller. So this is, I think, quite intuitive, and this is plotted for different values of the parameter, which I don't want to explain. Okay, so now I'll come to another. Put this a little more into perspective by looking at a charged scalar field. So remember this, we're talking about a charged black hole. So to make a charged black hole, you need some charged matter in the first place. So we should really look at a charged charged particles also on this space-time. And the easiest way to do this is to just go from a neutral, a real scalar field to a complex scalar field, which is coupled to the background charge of this black hole. And you then have a current, the current or charge current density, which indicates how particles flow in this background. And so the basic idea that you may have is that, okay, maybe you think of this charge, the background charge, to cause particle-antiparticle pairs to be created, like in the Schwinger effect. And then naturally, because this the singularities here are charged in the opposite way, you'd the positively charged ones, let's say, get drawn in this way, the other ones in that way. So this would be the classical picture if you really believe the Schwinger pair creation picture. It's not, again, a mathematically rigorous proof of anything, because for one thing, the time coordinate, this space-time isn't static in region 2. So you can't, if you're an observer, you don't see the geometry as remaining the same, but you view it as changing. And so this will, it's unclear how this will relate to this particle creation picture. So there's a similar theorem that the quantum current is given by a universal divergent quantum piece plus a relatively harmless state-dependent classical piece. It's a similar theorem. There's an expression for the C and so on. And there's a regularity statement about this remainder. Now you look at what happens. So here I look first at, maybe let me go to the very beginning. So you have here the event horizon, which is sort of the boundary of the black hole, the thing that we would see or would represent the boundary of the black hole when looked at from outside. And then there's the Cauchy horizon, which is the thing once you go inside, which separates you from the singularity. So first you can ask, maybe let's look at the current at the event horizon. So if you just stay clear, just stay outside the black hole, you maintain yourself just there, what you would see. And that's plotted here. So apart from lots of detail in this plot, there's one thing, you know, all these curves are positive. So that means the pair creation or the quantum current tends to neutralize the black hole at the event horizon. So if it's highly charged, the quantum current will neutralize it. It will carry away quanta of charge from the black hole. So, and it's plotted against the against the charge of the particle times the charge of the black hole background. So you see, if you think about it as a result of particle-antiparticle pair creation, it becomes stronger because if you create a pair with a higher charge, you can neutralize it faster. And also you see it gets weaker for more massive particles, which is also intuitive because it's harder to produce particle-antiparticle pairs. So nothing, this is all very expected. And there's nothing, I just wanted to show this is the expected behavior, and you just verify it numerically. So now look at the Cauchy horizon. It is totally different. So first of all, you can have a current going of negatively charged particles going into the negatively charged singularity. So it's something that is totally impossible classically, like a heat flowing from the colder to the hotter pole. This is charge flowing to the pole with the like charge. So this is represented by these curves which drop into the negative. But there's a safety switch, which is described by this inlaid picture, where you see that as you reach extremality, you see if quantum effects further and further charge up the black hole, you will push it across the extremality bound, you will destroy it. And you see there's this safety switch here that as you approach this dangerous place, you start to discharge again the horizon. So this is an inherent, at least in this parameter range, it's a non-trivial fact that you can't in any way easily see this at all from the equations. So I think it's a truly self-censoring feature of nature of quantum physics inside black holes. Okay, I have a slide, a summary slide here to highlight again the difference between the event horizon, which is the boundary of the black hole as seen from outside, and the Cauchy horizon, which is the boundary of the region with the space-like singularity that hides the monsters. And the key difference is that the current, the charge current, or the energy flux is infinite, is finite at the event horizon, and it's actually very small. Quantum, like it's a quantum effect, it's very, very small. And at the Cauchy horizon, it's enormous, it's huge, it's Planckian. The event horizon always gets discharged. The Cauchy horizon can get charged or discharged. The current increases with Q. It could decrease with Q. It's also a difference. And maybe the last one, it's the event horizon, the black hole outside. It's the expected, you have the expected steady state behavior, whereas at the Cauchy horizon, it's really totally unexpected and counterintuitive behavior. Okay, so we expect that there's a version of this for truly astrophysically relevant black holes, which are the Kerr de Sitter ones, where the current is replaced simply by the angular momentum density, and we expect strongly that we have exactly analogous results. And why we think that is because mathematically, at the level of description that we're working, there are many analogies between these scenarios, although there are also some crucial differences making this a much harder problem. I don't want to, so this in principle concludes my presentation, which to summarize is that black hole interiors are, I have something else. Just want to give the summary before I go into some more technical. I have until 10 past, is that correct? Oh, 20 past, yes. So I nevertheless want to thank you already here, in case you will be falling asleep and you won't hear that. I thank you at the very end of my talk, and I want to give you the summary, which is that charged and we believe also rotating black holes, generic states are steady states outside, so you transport charge and angular momentum and energy away from the event horizon to infinity in the expected way, whereas inside black holes it's very different, and you can have the quantum currents totally dominate everything, unlike at the event horizon where you have this very, very, very small quantum effects that cause the black hole to radiate by Hawking radiation. Just very dimly, you cannot see it. It's just such an incredibly small effect. Whereas inside a black hole, you get another horizon at which quantum effects are extremely large. They become Planckian, they become infinite, and they totally change the black hole geometry inside the black hole. I think something I think it's very important that quantum effects, though, cannot destabilize it. It cannot be a runaway effect. They cannot overcharge the black hole and turn it into a naked singularity. There's somehow seems to be a built-in switch. So this is based on mathematical theorems, the strategy for which I will say a few more things. And then there's some constants that simply have to be determined by a scattering problem, and that scattering problem at the moment is treated numerically, but maybe in the future it can be treated analytically too. Okay, so and I wanted to say a few things about the mathematics behind this, since after all this is about the interactions between mathematics and physics. So I didn't want to give you the impression that this is a predominantly numerical work. There's just this aspect of it that you want to compute for the physics at the end some constants. But the most part is actually mathematical. And what you do is you treat quantum field theory in curved space-time using an algebraic approach to quantum field theory as pioneered by Haag and Kastler and elaborated greatly by many people, among others, the group of Roberto in Rome. And for this type of linear field theory, somehow in the end, everything is inside the two-point correlation function because it's a Gaussian state. So in this sense, it's very simple, but the two-point correlation function is a very, very, very complicated thing. It's not just so it's, first of all, the two-point function of what one should think as a generic state. So there are certain generic properties that it should have. It should be a solution to the wave equation simply because the quantum field is, and it should reflect the commutators of the quantum field, which can be written succinctly in this way. These are sort of the Heisenberg, the canonical commutation relation in curved space. And then they should satisfy a kind of a positive energy condition. And in curved space, we understand now for about 20 years that the right general criterion is posed by a Fourier analysis, as in Arthur's talk, but a variant of it, it's a sort of a local version of it called micro-local Fourier analysis or micro-local analysis invented by Hermann de Droestermaat, and this is the engine behind many of these results. So it's condition on the so-called wavefront set of this thing, which is supposed to consist, is a subset generically of the cotangent space, and it should be the xk and x prime k prime should be on the same bi-characteristics, and the momentum vector should be future pointing. And one consequence of this that comes out of the well-known procedures then how to obtain the stress tensor from such a two-point function is that this expected expectation value of the renormalized stress tensor is a smooth function on space-time. So space-time doesn't contain the horizons, the Cauchy horizon, so it may still, it's a smooth function on the open part, the interior of the space-time. Okay, and then another aspect of this work is to define a particular state called the unroot state with a particularly chosen two-point function, which in some sense projects onto the positive frequencies in a particular way. I don't want to describe it more. And then the strategy is to show that this reference state is a Hadamard state and to estimate the difference between it and an arbitrary state, an arbitrary Hadamard state. So there, that's where really the hard analysis comes in. So first there's a fairly deep result on wave propagation on this causal propagator in this background, relating it to the spectral gap. That's from more or less from Hinz and Barty's paper. Then in Kerr, the spectral gap is known to be positive in Weiser-Nordström, de Sitter, and in Kerr. It's a very hard problem to prove that, but I believe it to be true. There's some recent work on this. This is all, then it becomes very algebraic, complicated in relation to integrable systems, things like that. Then if you have this, then this two-point function is a well-defined distribution in the first place, and you prove the commutator property based on these two results. And then to prove the Hadamard property, you use the propagation of singularities theorem for the wavefront set. Actually, that's a very sophisticated version. This is already used here. So this result itself is using crucially the microlocal analysis and the Melrose-Vargy extensions thereof. And then the Hadamard property of this unroot state and what one knows about the difference between the unroot state and a generic state gives in the end the theorem that I've shown. And then what's left is a numerical evaluation of scattering coefficients, which is done on a computer. Well, no, I mean, this also requires a certain amount of mathematical knowledge about these ordinary differential equations, which have regular singular points, and how you go about. You have series representations of solutions in terms of hypergeometric. Anyway, it's also a little bit complicated, but in the end you obtain these curves. And with that, I now finally want to thank you again after this appendix. I'm happy to answer questions.
Many thanks to Stefan for this nice talk with appendix. And please, Arthur.
So I really enjoyed your talk because I hadn't heard about this before, but I have a three-part question, and maybe the parts are related. First, when I think about quantum field theory, I'm used to using the path integral approach. And there, in the one-dimensional time problem, Brownian paths are wholly continuous with exponent less than a half. And I think that's just the condition you talked about for the cosmic censorship. And therefore, I wonder if those two are related. That's question one. And question two has to do with, well, for the free field, you have these estimates, but can you do anything about interacting fields?
Oh.
And in the constructive field theory case for examples that exist in 2 and 3 dimensions, you get some control over the continuity of paths. So if the continuity of paths is connected to this cosmic censorship, can you say something about that? And well, that's really encapsulating my third question too.
So maybe I can answer the second question first. If you could you switch back on the presentation? Yes. So you asked, one question was what you could do about interacting fields, and let me first answer why you actually should do something about interacting fields. Well, first of all, already the linear fields show this terrible divergence. So nonlinear equations are not going to behave any better, for sure. So in this sense, this answers the question. But there's a question about the universality of this divergence. So for free fields, this constant C is independent of the state. And that's not so clear for interacting fields. And that would be, I think, interesting to look at. Whether you can do something about it is less clear to me. You have to do something in perturbation theory because these micro-local techniques, Fourier analysis, local Fourier analysis are so strong that you can probably treat terms in the perturbation series to arbitrary orders. Now, about your second question, I would also like to show something. So the Euclidean approach that you mentioned would straightforwardly apply to region 1. Why? Because the time coordinate, this t, is time-like here. So time increases t, the coordinate t increases from here to here. It doesn't apply, at least straightforwardly, in this region because the time coordinate counterintuitively goes this. So the t coordinate here goes from here to here. That it doesn't. It's not a causal pathology. It's just that this coordinate, which makes the metric static and which you would need for the Osterwalder-Schrader reconstruction, is not a time-like coordinate here. So what to do about this, I don't know. And I don't think, I know these representations that you talk about are extremely mathematically very powerful and very useful for many things. But I think they don't particularly tell you anything about the Cauchy horizons because the regularity of the paths in the path integral would also apply in this region here, 1, where there's no divergence of any kind of a physical quantity.
Any further question?
Look divergent. I mean, do you have any? The final result is finite. Do you need some sort of renormalization or?
Could you show again the slide?
Yeah.
No, it's not. It's not divergent because this decreases exponentially with the L. So this thing is already fully renormalized. So we're talking about the renormalized operators.
And the other question is a curiosity. You studied the case of De Sitter. You can do the same, play the same game in anti-De Sitter space. And
yes.
Have you tried this?
That's a very good question. You could do it. So De Sitter space is particularly interesting for the reason that at the classical level, the cosmic censorship is violated, so you really have a problem. In anti-De Sitter space, I don't know, would be very interesting. And also one doesn't there, I think, have such a clear intuitive explanation for why, if at all, it would be violated classically. Because here you have the cosmological redshift, which is the competitor. And so you can see this competition also in this ratio, because this alpha is due to the redshift and the kappa minus is due to the blue shift. So you see it's the competition. Whereas if the cosmological constant is opposite, it's less transparent, maybe what you would expect.
Okay, thanks.
Thank you. There is any further question? Please.
Yeah, thanks again for the interesting talk. I was wondering, in the case of a charged black hole, you said that at the Cauchy horizon, you can have the effect that also the quantum effects charge the black hole up. So you have a negative charge flux, but it always has a safety region where you have a positive one at a high charge ratio. Does it mean you have a stable point of charge where you always get to after some time, or how is it, should interpret this?
Yeah, of course, this doesn't really take into account the back reaction. So in this sense, it's the results are rigorous. But to answer your question, you'd have to let the quantum stress tensor back react onto the metric, which is something that we haven't done. But if you just maybe intuitively, I think what would happen is the quantum effects charge it up, charge it up, charge it up to a certain point. And then it reaches a certain equilibrium as a very highly charged black hole, where this charging up was due to quantum effects. It would, but what exactly would be then the nature of this singularity that develops here? I think one cannot easily answer with such a simply heuristic argument.
Okay, so is it really then related to the charge of the black hole, that you would say, at least in this setup, black holes would always end up with a high charge?
Yes, I would say that, at least in the parameter range that we've studied numerically. Of course, you have Q, the charge of the black hole, you have the mass of the black hole, you have the mass of the scalar field, you have the mass of the charged particle, and you have the cosmological constant. So it's a 5-dimensional parameter space, which we explored numerically. So we didn't explore it completely. So it's shown in this. It's shown in this plot for the cases that we were able to study. And there your picture is right.
But in a realistic situation, you would always expect that black holes have a very low charge, right? So where is it that this kind of setup doesn't explain this?
You see, there are cases where you have only charging down quantum effects. So it really depends on the parameters of the black hole.
Okay.
If you push it beyond a certain range, it will charge further up, charge up, charge up, charge up. But it said, according to this inlay, at least for those parameters, it would saturate somewhere.
Oh, okay. Yeah,
but
thanks for
in
that.
this case, it will charge down, for example, which is the expected behavior.
Yeah, thanks for the explanation. Very interesting.
Yes, maybe a related question. I mean, you have this point where the constant becomes zero. Do they have a significance, or?
Yeah, here I give the answer of the mathematician. It's a set of measure zero, so I don't care about it. But I don't want to sound condescending. In fact, I wonder if I give this. Yes, in fact, also in answering your question about ADS, there's a 3-dimensional black hole called the BTZ black hole, which is very, very popular in theoretical physics, because many things can be calculated exactly. And also these curves somehow can be calculated exactly. And this was done by Diaz, Real, and Santos. And they found in this case, it's exactly zero, as you say. So there's no quantum effects don't act in the way that they describe in 3D. It's also an ADS type black hole. But this is not in contradiction with what we do. So our analysis would also carry through in 3D, and we would also get exactly zero. So you see, though, that it in this kind of very, very special situations, you can occasionally get zero. And this is why it's non-trivial to plot these curves.
But I mean, can it be considered like an equilibrium point because you grow?
No,
and
it's
then-
not. No, it's an unstable point. You see, because here you will, if you're just a little bit away from it, you will. Quantum effects will change the charge mass ratio, and you will go either in this direction or that direction. So it's not a stable point.
Thanks.
There was just a similar question from the chat of Zoom, so you answered. Thank you. Okay.
I answered it. Very good. Very efficient.
No more questions? Is there no question online? Ah, there is a question.
So we expect that black hole become unstable for larger values of the charge. How can this change this picture?
No, I don't think I said that. First of all, the exterior of the black hole is always stable, and the interior is not really unstable. According to our results, it can charge up to a certain point, but it cannot destroy itself. So it is no runaway effect, so to speak. So in this sense, it is at least in the range that we were able to study. It is still stable, but as it undergoes a large qualitative change.
I have a question. If there is a relation between, the strong cosmic censorship, at least in this case for generic quantum fields and Hadamard states, and the quantum focusing conjecture proposed by Busso some years ago, and the others, which relates the average of the stress energy tensor with the relative entropy of a suitable region. If there is some kind of relation between the two, and if one then can get some kind of estimate of the entropy near the Cauchy horizon in this case.
Yeah, this is an interesting question in many ways. So we tried to find at first some thermodynamic explanation, and we, however, could not. So it seemed to us that the details of the dynamics was important. However, so if you integrate this along a null line in the v direction, you get the quantity that's called the average null energy operator, or the NX operator, or its expectation value. And as I said, the C can have a plus or minus sign depending on the parameters. So in one case, you get a very, very large violation of the NX. I don't think this really contradicts the consensus in quantum gravity that this condition is somehow satisfied, because it means that you have a huge back reaction, which you should somehow take into account. And I bet if you do, then it would be your end, the metric would be so drastically violated really that somehow you'd, in some sense, you'd satisfy it again. But it is clear that just in quantum field theory without back reaction, it is not a general theorem in curved space, but it is a theorem in flat space, or if you are in a null direction along the horizon, like here, if you move along this horizon, or if you move along that horizon, it will be a theorem. But if you move across the horizon, it is.
No further question? If not, we thank again for Stefan for the talk and for the discussion. Yeah. Now we move to the other room for lunch and